Okay. Okay, as always, don't forget to type in your name for attendance. Okay. All right, let's get started. Last time we were looking at electron configurations. Anybody have any questions about anything there? No? Okay. All right, so we have a test 3 review, which I'm going to open because it's pretty much, we're done except for a couple of things, which I want to make sure that we have that in here. I'm going to download it and type it in. Okay, so the answers are already on there all the way to the bottom, but I still want you to be able to answer them. So before you actually do them, see, they're all back there, but don't look at those. Not yet, anyway. All right, so for this one, I want to, let's see, make it bigger so you can see it for one thing. All right, so a packet of light is known as a photon. There's a bug on my screen. Sorry, photon. There you go. Make it red so that you can actually see that. Change the color. There we go. Okay, the state at which all electrons in the atom are at their lowest possible energy level is known as the ground state. Why is it changing color? Okay, anyway. And then when an electron jumps into a higher level, the atom is in its excited state. Oops, excited state. Okay. Okay. The scientist who applied Einstein's, hold on, better write you guys down before I don't. Okay, there we go. All right, the scientist who applied Einstein wave theory to the electrons, his name is de Broglie. I think it's Louis. always know the last names, but the first names, I'm not so sure. I think it's Louis de Broglie. Change color. There. Okay. Okay. The theory that it is impossible to know both the position and speed of an electron simultaneously is known as Heisenberg's. Okay, hold on. Okay. Heisenberg's uncertainty principle. I was getting there. Sorry. Heisenberg's. Okay, so that's his name. By Warren. I think I do know that guy's name. Warren Heisenberg. They came up with that. Theory that no two electrons can. Okay, let me see who's coming in. All right, I already let her in. I don't know what happened. Okay. Okay. There are no more in the waiting room. No. Somebody. What did I miss? See, this is why we want to write our name. Jasmine, I think it's you. Yep. Nope. It's not you. Okay. Okay. Who else? Kennedy.
Miss Vides,
Yes, ma'am.
one of the assignments due, I think it is a discussion. I think the link, it won't open because it's saying that you need to be a Southern University student.
What?
Yeah, I could show you after.
That's crazy. That shouldn't.
Like there was asking for the email to
Okay.
access the PowerPoint.
Sure.
It's for the periodic discussion.
That's weird. Shouldn't do that. That is so strange. Okay. I'll take that under. I'll look at it and see why does it say that? Because it shouldn't say that.
Thank you. Thank you.
Sure. Thank you for letting me know. Okay. One more. Always have to find who it is that's on here. That's bleeping. Okay, there you go. Okay. All right. So remember to put your name on the chat so I can take attendance. All right. All right. So we were saying that no two electrons in an atom can have the same quantum numbers. That is the Pauli's exclusion principle. Instead Paul. Yeah. Sorry. All right. The next one, the one that the electrons fill the lowest orbitals first, that is known as the Aufbau principle. And I am not German, so I don't know how to pronounce that. But basically, what I've been told, Aufbau or Aufbau, whatever, means that exact thing. And then the theory that are within the sublevel. Okay, let's see who that is. Okay. Within a sublevel, they are occupying their own orbital. That is known as Lord Hund's rule. Okay, so these are all of your answers. And if you look, like I showed you, they're already there. But when you're studying, you should not be looking at them, right? So the term that describes the outermost electrons, that is valence electrons. Okay. Positively charged ion is called a cation, and a negatively one is called an anion. We went over that. So all of these, you guys are ready for this test pretty much. So that's why I'm going over this again. All right, next part, the most stable type of electron configuration, that is known as what? We just went over it. No, nobody knows. Okay. Well, that one is right here. Like I told you, all the answers are right here, but we just want to make sure that we don't, you know. So it is a full energy level, remember? So that would mean it would be like your ground state or the full energy level. So full energy, oops, full, sorry, my fingers are falling in the wrong place because I'm holding a pen in my hand so I can be writing who's walking in as I'm trying to do that, but I still miss a couple of you, so make sure that you write your name on the chat, please. Okay, the lower left-hand side. Okay, so this one, lower left-hand side, period of the elements, most of the elements, that's the metals, right? The other one, and by upper and lower, I think what it means is in number. That's the non-metal. Then you've got the section with the D block. Those are transition metals, right? So every transition metal has a D electron, so at least one. The section that is the S and P, these are known as the representative elements. Or there's another name for them, I can't think of it right now. But that's one word. Main group, that's the name. I couldn't think for a minute. It's the same thing. Okay. A 3D region where the electron is likely to exist, that can be interpreted as either of two things, either the electron cloud, but you notice it says region where an electron, okay, so that I would say that's an orbital. The way that they're describing it, the way that I'm reading it, but it could be also, it could be, like I said, referring to the cloud itself, which is made of orbitals, so could be either one. I don't want to go that far. Okay. Sorry. I didn't want to go that far yet. All right, there we go. Hey, Desiree. Okay. All right. All right, so the process by which the core electrons partially block the attraction between the nucleus, that is called electron shielding, remember? I think that's about all of the ones that are word answers. Okay, now drawing orbitals for the following elements. Okay, so they want us to draw the actual orbital diagram. So I cannot actually draw them without using my finger because it's hard. I cannot put arrows in there. So I'm going to draw one at a time. All right, so magnesium First of all, we need to know magnesium's long form configuration in order to draw it. So for that, we need, oh, look at that. I have a new toolbar, except I need net. There. Okay, so there we go. So we're going to have to draw the orbital diagram first. So the 1s2, 2s2 thing. So we're going to draw it. 1s2, ooh, my finger. 2s2. And it's magnesium, so it goes all the way to, okay. So 3s. Okay, so then the next one is 2p6, right? And then 3s2. That gives us exactly 12, which is correct. Now the orbital diagram, remember, this is your 1s, that's your 2s, oops. That's your 2p, all of these, right? And this is your 3s. And what you do is you just draw your arrows. These are going down, sorry. And then this and this, and that's it. So if you want to draw it pretty, you have a hand. So I've got a screen and no pencil, so it makes it very hard for me to draw it. Okay, so that's how we do it. That's one. Okay, and the next one's silicon. So silicon makes it very easy because silicon is just adding a 3p, right? So we need 3p to add there. So we just need another 1, 2, 3 over here, and 3p, and then 1, 2. So all right, you see? All right, so that was that one. And then the next one is titanium. So titanium finishes this one. And for that one, I'm going to redraw because I'm running out of room. So I'm trying to see if I can redraw smaller, but it's hard. It's very hard to do it much smaller. But for titanium, you would actually have to add to this one, you would have 3p6, then 4s2, and 3d2 because it's titanium. Right. So 3p, 3p's would be here. This would be full, right? Then you have your 4s, and you'd have your d's, which is 5 of them. All of these are your 3ds. And you'd have 2 on this one and 1, 2 on that one, and that's it. So that would be titanium. So that's all of your configurations as they are. I want to see if my stylus would work on this one. I've never tried it. Okay, I got the stylus. Let's see if that works better. All right, so I actually did these, with my hand, which is not the prettiest thing in the world. So we're going to go ahead and clear them. Okay. Not letting me. All right. There is a new toolbar, it says. So there it is. Okay. So just trash it all. Clear all my drawings. There we go. All right. So the next thing, and hopefully it'll work. All right. Is to do the longhand configurations for all of these elements. Okay. So for that, nope, it's not working. It doesn't like my stylus, so I have to use my finger. Okay, well, actually, I can use a typing thing. I think I'm gonna do that. I'm gonna do text. Of course, you're gonna have to lift the 1S2 like that, right? Above. Then the next one is 2S2. And it's nitrogen. So nitrogen is just gonna be 2P3. Okay, like that. So basically these are raised up. Let me see, will that do it? No, it won't do it. Okay, so that's that one. And you know what? I think I know what I'm gonna do. I'm gonna erase all of these. I'm just gonna type them in because I can. Nope, I want my mouse. There we go. I'm gonna type them in because I think it's better. Yep. Because these are superscripts, so that's why I'm doing that. There we go. And that's the last one. Okay, so that's the long form, right? For that one. For potassium, it's going to be 1S2. Oops, where did you go, potassium? Why did you fall out? Okay. Then you got 2S2, 2P6, and 3. Let's see, S2, we're going all the way to 4. 3P6 and 4P1. All right, so all of these are elevated. Remember, that's why I'm doing it this way. So that is your next one. And you should already know how to do these. Remember, they are just the periodic table, following it along. Know where your P's, your D's, your S's, all of those are, and how to write them. All right, chromium is going to go all the way to the D's. We said that anything that is a transition metal is going to have that. So I'm going to be smart, and I think I can do this and then just paste it so that it gives me the whole thing. Let me see. Haha. There we go. No. Okay, that's good enough. No, I don't have to rewrite it. You notice that chromium is, come on. Why are you erasing? Trying to put this one up there, but it won't let me. That's fine. All right, so it's 4P6 would be next, right? No, that's what it is. I know what it is. It's not what I wanted to do. So let's undo that and paste the real thing. See, it won't. Undo. There. All right, there we go. All right, so that would be 6 there because we're going beyond. No, there's no 4P. Never mind. Nope. There's no 4P. There is a 3D though. Okay, so there is, did I say 4P? I meant 4S. That's the problem. I was like, something's weird. There we go. I put 4P out of habit. All right, so the next one is 4S. 1, in this case, is 2. And then we have 3D in chromium is 4. But remember these exceptions that we talked about? This is one of them, because the 2 is so close to being halfway. I mean, not the 2, but the 4, sorry, is so close to being halfway full that what it'll do, it'll change one of those to the D right there, okay? And that's what it'll do. And there is your electron configuration, the long form for this guy. All right, these are the 2 that we just did. Where am I? There's no, that is supposed to be 5. There we go. All right, so now the shorthand configuration. Okay, so the first thing that you need to do is locate the element, right? Find out which noble gas, put it in brackets, not that brackets, these brackets. All right, so antimony is on row 5. So you're going up 1 to row 4 and all the way to the noble gases, and you find krypton there, okay? So krypton, and then after that, you just keep going. So after krypton, we have 5s2. We haven't gotten antimony yet. So 5s2, we still got to do 4d10. We still haven't gotten to antimony yet. We still have the 5p, and we've got antimony. We've got 1, 2, 3 for 5p3 for that one. So this is the short form for the electron configuration for antimony. And if you count the electrons, remember how we did that? We said that krypton has 36. And then we add the rest of them, and that should give you the exact number of 50. No, not 50, sorry, 51. So 36 plus 5 is what? 41 plus 10 more? 51. That's correct. All right, bismuth, same thing. Okay, so who wants to tell me what noble gas to use? And put in the chat, it's fine. Which noble gas do we use? Which one? Right? Nobody wants to say anything. Okay. We shall do it. All right. So let's look at a periodic table and determine, because that's the best way to do it. We have to look at a periodic table. So I'm going to go and look for it right here on your, actually, it is easier to go to, nope, I don't want to go to Moodle. Nope. Sorry, I meant to hit this and it just slipped. All right, and we're going back to your canvas. And there's a periodic table on here, so we're gonna go grab it. All right, and it's under module. So let's go, come on. All right, periodic table. That is right on this right here. Nope, not that one. Periodic table with, not the one with ionic charges. We don't want that one. We want the periodic table that we have. This, I think it's above that. There it is, color periodic table, PNG. All right, this one. All right, so let's make it bigger. And we are trying to go to where? We are trying to go to, oh, nope, we cannot use that. I have to use my finger. All right, we are trying to go to we said we did antimony, but the next one was who? Well, let's go find out. All right. Remember, we're looking at these. So the next one was, oops, not you. All right. We said we were going to go to bismuth next. Bismuth, then technetium, then germanium. Okay. So let's do bismuth. Bismuth is right here. Okay. So bismuth is here, right? We are going to go up and over. That is xenon. And then from there, we're going to go these guys, right? So that'd be 6s, 2. And then all of these guys right here. So that'd be 4f, 14. Then all of these guys right here. So that'd be 5d10. And then finally, we have 6p3. Because there's 1, 2, 3 before we get to bismuth. See that? So that's the configuration for bismuth. All right. The next one would be technetium, you said? Okay. So technetium's TC, he's right here. All right, let's erase this guy. I'm getting used to the new periodic, the new controls that they've given us, which is fine. All right, so technetium's right here. We go up and over krypton. So we use krypton as our noble gas. And from there, we have to go through these guys, right? So that's 1, 2, 3, 4, 5. This is 5s, 2. And we don't have D's, P's, but we do have D's. And that would be 4D, and then we count. 1, 2, 3, 4, 5. And there you go. That is technetium. Okay, so far so good. And I forgot what the other one was. Sorry, my brain is not working today. What was the other one? Technetium and germanium. Okay, so germanium is the last one. Let's go back to the periodic table. All right, so germanium. Let's clear this. All right, germanium's right here. So we go up and over. That's argon. Then from there, we still have these guys, which is 4s2. We have all of these, right, which is 3d10. And we count 1, 2. So it's 4p2. And again, if you wanted to do the math count, you can. See, germanium's 32 electrons, right? We have 18 from argon. And if we add 2 more, that's how many? That's 20, 30, and 2. And that's exactly how many we have, see? So that's what you have to remember. So 18, right, from argon, plus 2 is 20, 32, see? And there it is. It matches what we wanted, which is 32. And that's that one. Okay, so let's go back to, we're going to leave the periodic table on there, just in case we need it. All right, clear all those drawings and go back to this one. All right, so next, we have to do the, okay, we were doing that one, but we're done with those. So next one would be to do the ion symbol. Okay, now this is the part we haven't covered yet, but it's easy. It's very easy. Remember how we do electron configuration, right? So basically, we just look for the electron configuration for the element. And in this case, for tellurium, let me write it down by actually typing it in. All right, so it's going to be 1s, no, it says shorthand. Sorry, I need this guy first. Who just walked in? Hold on. Okay, so tellurium, right? It is going to be Te. Where are you? There you are. Okay, so you are krypton. Close the thing, right? And then we've got, from there, we have 5s2. Oops. What is that B? Did I hit that B by chance? Oh, nope. Enter. Oh, nope. Okay, undo. Hold on. There we go. All right. 5s2. And then we've got all of the D's. Yep. 4d10. And all the way to tellurium would give us 5p4. Okay. So that's tellurium itself. Now, if we were to change one thing, and I'm just going to put these up so that you see them better. Oops, both of these, not just one. Come on. There. All right, and the last one is 4p4. So that would be how it would be for tellurium itself. Now the tellurium ion, being on group 6a, we know that tellurium, the ion, is going to be Te, right? -2, which means that when you add those extra 2 electrons, they're going to fall in the one area where they can, which is right here. And I'm going to change the color and make it 6. So that's the ion. You see that? Okay. The next one is boron. Boron is helium. And it's going to be 2s2 and 2p1. All right. So this is okay. All right. So I want you to see. This is boron itself. Boron ion, since it is in group 3A, is going to be B negative, positive, not negative, positive 3. All right. Now, what's going to happen here? Interesting, right? The one thing, oops, come here, you. I didn't want to highlight you. I want you to go up. There we go. All right. So since it is a -3, that means we are losing these 2, right? So the actual boron itself is not going to be helium. You can't have a noble gas configuration for your configuration. So you actually have to spell it out, which is 1s2. That's the difference between these two. When you add, it's easy because you just add. But when you subtract, you actually have to go back and give the configuration that you have under there. All right, so this one is barium. Barium is xenon. Okay, and then it is 6s2. Okay, so 6s2, that's barium. The barium ion is going to be Ba plus 2, right? Which means, we're going to highlight it also, but we're also going to bring it up. Okay, which means that this guy is going to be gone, but we cannot have xenon as its own electron configuration. So what we're going to do is we're going to give the shorthand configuration for xenon, which in this case is krypton. I know it's weird, but that's how it works. Krypton, oops, I keep doing that, krypton. And then after that, it would be all of the stuff before we get there. So 4s2, then it would be 3d10 and 4p. What is it? 4p, what are you? 6. Yeah, because it's, okay. So that's the actual configuration for xenon itself, okay? The shorthand version. And that is also the one for barium ion. All right, bromine. Bromine is easy because this is a negative. So bromine, you just look for bromine and it is argon, right? So we go AR, oops, one R, little r, okay. Then we have, after that, we need to go to 4s2. Okay, so 4s2, 3d10, and 4p5, right? That would be the actual configuration for it. Since this one doesn't gains electrons, it doesn't lose electrons, we don't have to make any changes except for one thing. The bromine ion would actually have a 6 here. I'm going to change it. We're also going to change it to 6. Okay. And that is the configuration for bromide ion. So it's not bromine ion, but it's bromide ion, Br negative. Okay, so it should be in black. All right, and the one thing is this needs to go up, and basically that's that. So for potassium, same thing applies. Potassium is argon, right? Except this time, see, this is the thing. When you have one that loses, then you have to modify your shortcut because it is argon and it is 4s1. Very simple. Okay, that's your potassium. But potassium itself, the ion, is K+. Which means we're going to lose that one electron. And the one electron we're going to lose is this guy right here, right? So in order for us to give that electron configuration, we're going to have to do the shortcut configuration for argon, which is going to be neon, right? Like this, and just 3s2 and 3p6. And that's that right there is argon, okay? And that's how you do it. That's how you do all of those. So as you can see, we do have to modify it when it's positive. So that's why I've been highlighting the positive so that you realize that there's a difference here, okay? The other ones I highlighted the change, that's it. But for this one, we do need to highlight that it's positive. So then the whole change becomes this entire thing. The whole entire thing I'm going to make red. Oops, except for that, I didn't make it red for some reason. Okay, there. So that's the whole entire thing that you're, see this one too. That's the answer. This is the modification you have to make. Whereas in the other one, all you modified was the number when they're negative. Okay. Now for this next question, it says, which one of these has the larger atomic radius? Remember, atomic radius increases going, sorry, I need to get this pen, right? Like that. That's how it increases. So if you look for carbon in tin, you can see that carbon is not the largest. It is tin, because tin is below. So let's highlight it and give that as the answer. Well, let's just highlight it with this thing. Highlighter. There you go. It says this is a highlighter. I don't think so. It says it is, but maybe I need to make it thicker. There we go. It does highlight. There we go. And then strontium or indium. Okay, so we have strontium all the way across to the left, and indium is sort of in the middle. So it's going to be strontium because it increases going this way, right? See? Then this, it says to large the atoms from smallest to largest. And you've done this in that one, exercise, that homework we had. All right, so lithium, potassium, and it's still atomic radius. So you notice that I'm showing you the way to go. So potassium would probably be the first one. No, cesium is. Sorry, I didn't see cesium. Cesium. That would be the largest. Sorry, the largest. So largest first. Yeah. So it's the opposite, like that. Smallest to largest. So oxygen first. Then it would be lithium, right? Then potassium, and then cesium. Cesium's the largest. All right, on this one, iron, phosphorus, radium, and tin. Not titanium, sorry. I thought he said, okay, titanium. So these are all in there. The one that's the most is radium, okay? So we'll leave that one alone. Iron, which one is the farthest over? I want to see. Titanium, nope, that is not it either. So it must be phosphorus. Yep, phosphorus is it. So phosphorus first, right? Then that would be, next would be probably iron, because titanium is right next to it, but a little farther over. And then the last one would be Ra. See? You can actually do this. Oops, I know that was a highlighter. No, this is not the actual answer, so let me clear these out. All right, so this one, when you look at these, okay, what do you see? Okay, we have let me just highlight her again. So this one was tin, and this one was strontium, right? Okay. All right, for these right here, the largest ionization energy is exactly the opposite. The only one that goes the same way is this way and up, okay? So, francium or neon? Obviously neon, because francium's the lowest of all. So it is definitely going to be this guy. And then we have sodium or silicon. Well, silicon is farthest to the right, so it's got to be silicon, right? Okay, now, smallest to largest, again, same thing, just do that. Now, the melting point and boiling point, we're going to skip those, but these they have to do with the d electrons, so cesium versus tungsten, iron versus iron, so obviously iron is going to be the highest, tungsten's probably going to be the highest, and sodium or silicon, that is, Well, one's a non-metal, so sodium probably. Let's see. And which particle has the largest radius? Okay, again, this one, because we know that ions decrease when they lose electrons, but they increase when they gain them. Okay. And then there's your answers, all right there anyway. See, like I said, tungsten, iron, and silicon. I said sodium, I meant silicon. Silicon's more likely to have, as it also has the electrons. So, all right, so there you go. So these are a little bit more complicated than just looking at them. That one is a trend, yes, but you have to look at it a little bit closer to that because of the way that they are. So if they have d electrons, it's going to be, you know, like the transition metals. But then you've got sodium versus silicon. Sodium has less electrons than silicon, so that's one of the reasons. All right. Okay. So that's it. Basically, if you look at your, let's see, let me go back to stop sharing that. And let me go back to sharing the one thing that I want you to see, and then you guys can go. All right, so great. That's not what I meant to close. Not cancel. Let me just, yeah, no, don't save. Right, that's where I wanted to go. All right, so from here, this was like a study guide kind of thing, reminder, right, of what to look at. And that's the review. Don't forget to do the extra bonus. That will give you lots of points. This one right here, it'll give you lots and lots of points. And the test 3 is open and is due October 20th. I mean, you got a long time, but you know, it is open. So this is the tests in case you want to know how many questions. I can tell you there are 50. Okay, 50 questions on this one. But they're much more simple than the other ones. These are just, see, they're just plain questions about what we've done, all that we've done so far. So nothing too crazy. And that's it. Now, if you all have a question or anything, and you need me to explain something more before you take your test, I'm here. If you need me, just let me know. But we're done. Hopefully I will be seeing you next week. I didn't want to come right now because it looks like rain and my car is my son's car, which is not the best at all. And as long as it doesn't rain, I think it'll be fine. But it has really weird visibility, and that's why I don't like it. So, all righty. That's all.